So the topic, as I said, is going to be about I/O systems. So we have completed the role of operating system in the management of various components, like how operating system manages memory, how operating system manages the CPU, how it is managing the files, and now we are going to finally discuss the role of operating system in the management of I/O resources. So there are a number of I/O devices available with the computer, and the OS is playing a role in the management of those resources also. We will get some details about that particular module of the operating system from this discussion. So basically, the computer has got two types of functions. One is processing, another is I/O. Processing is nothing but the executions. So whatever you are executing in a computer, they are all coming under the category of processing instructions. Another different aspect of that is involved is I/O. So I/O is like a user interaction. So when processing needs to get some input from the user or has to provide some output to the user, that is done with the help of the I/O. So the OS is also taking care of the I/O, and it provides a lot of I/O services to the user, and it puts a bridge between the hardware interface and the computer applications. So, like for example, even if you take a C program where you want to deal with the keyboard input, you need an interface. Okay, you need an interface between the keyboard and the program that you have written. So that is done by the operating system, and we know that it is technically it's called as a system call. So whenever you want to access the keyboard through scanf, then it invokes a system call, which is a model of the OS, and then the necessary input is retrieved from the keyboard, and then it is supplied to the program. So the control of devices connected to the computer is a major concern of operating system designers. The reason for the difficulty in managing I/O devices is that they are of a very different nature comparing to other devices. For example, when you say memory management, a computer has got one single memory of a particular type. That is, if you take a RAM memory, primary memory, it's either a DRAM or it's it is having a particular characteristics, and the OS can be customized accordingly. But I/O devices are all different nature. For example, you have synchronous devices, asynchronous devices, blocking devices, non-blocking devices, and the speed of the device could differ. A wireless, wired device. So the nature of the devices vary drastically. As a result, writing code for managing all of them is very difficult task. That is why this particular model of the OS is one of the most complex management of the operating system. And when you talk about I/O devices, device drivers are inevitable. So device drivers are codes that are written for a specific device. So they are like the interface between the operating system and the device, because the operating system cannot be expected to have the knowledge of every device. Connected my Bluetooth device headphone with the computer. So it may not have that necessary code for handling that. So the device driver is installed to the OS before the usage of the device, so that it gets the knowledge. So it is like a evolution. So the operating system is evolved to include the knowledge of a new device by attaching or installing the device driver. And so I already pointed out there are many kinds of devices, and some of the devices are storage devices. There are transmission devices like the network connections and Bluetooth, and there are also human interface devices like the screen, keyboard, mouse, and so on. So they all have to be managed. And also we have the cabled and the wireless devices also. Okay, now the first idea is bus. So a bus is the okay. Before bus, we need to know what is a port. A port is the interconnection point. For example, if you want to connect a USB device to your computer, you need to look for the USB port. If you want to connect a HDMI cable to your computer, then you have to identify the HDMI port. So a port is it's a place or it's a connection point in your computer to which you can connect something. Similarly, for audio, you have got the 3.5 mm audio port, so through which you can connect to your headphones. So basically, a port is the connection point. And once you have a connection point, now you can connect your device with the computer. And that medium of connection is called as a bus. A bus is some more like a cable or a wire through which you can connect any device with the computer. It can be a single wire or a set of wires. If you are just connecting, for example, a headphone, it is just made of a single wire. But if you are connecting memory with the processor, it's either 32 bits or 64 bits. Accordingly, the width of the cable will also differ. So it will comprise of a number of wires to transfer n number of bits parallelly from one device to another device. So we have got the buses of various width. And it's a point of MCQ point of question. Daisy chain. See, daisy chain is nothing but interconnection of a set of devices together, so that it forms like a chain. For example, here you have got all the 5 devices are connected together. So whatever is transmitted by one device is going to be visible to all other devices. So that is the idea, and we have to specify the address of the destination. Only then the actual recipient will receive the message. Otherwise, everybody will receive it and assume that it's meant for them. So it's called as a daisy chain. Okay, and this is one popular bus architecture called a PCI bus architecture. So PCI, which will be explained in the next slide, it's one standard of bus. I think it was proposed by Intel. So it is just talking about how you can interconnect the components of a computer together. For example, you can see here is that this cable runs across the board, and processor, cache memory, main memory, the disk memory, keyboard, they are all interconnected into the bus, and as a result, anything can communicate with anything else. So if processor has to send an output to the monitor, it will send that data through the PCI bus to the monitor. So that is the idea of a PCI bus. This is the actual board, PCI board. The sample screenshot is provided here. Now, some characteristics of PCI bus are provided. So PCI bus is a common bus system widely used, and it goes on to detail about the individual components used here, which I just leave it to your reference when you go through the PPT. And there is something called as a controller. A controller is in charge of a number of devices. It's a terminology. A controller is in charge of a set of devices, so that whenever CPU wants to interact with or make use of any one of those devices, it will send a request to the controller, and the controller will in turn contact the device. It's like the counselor in your ward. So he is a representative. So whenever the government has to send something, implement some scheme to the people, they will communicate with the counselor, and the counselor will in turn discuss with the people. Similarly, the vice versa. So similarly, the controller will act as a coordinator for a number of devices, so that the CPU can deal with the controller, not with the individual devices. So for example, you have something called as a disk controller. The disk controller takes care of a number of disks. So this is, and whenever a request comes from the CPU, it's received by the disk controller, and then the individual disk which is involved in that request is then interacted by the controller. Now, there is going to be a question for which we will try to answer. How can the processor give commands to and data to a controller to accomplish an I/O transfer? So the question is that, so we understood that for any device access or any I/O access, processor only has to contact the controller, not the actual device. But the question is that how the processor can contact the controller, and also how it can share the data which needs to be further transmitted to the device. So that is being discussed here. One answer is that it can be done with the help of registers. So there can be some set of registers. The processor will simply write the requirements into those registers, which can be accessed by the controller, and controller understands what needs to be done. So there will be, in this case, there will be special IO instructions. So whenever the CPU wants to perform an IO operation, it will make use of the IO instructions, and it will transfer the data through the registers. This approach is called isolated IO. So isolated IO is having separate instructions for IO and separate instructions for memory. They are not going to be confused. There is another way of approaching this called memory mapped IO. In memory mapped IO based operating systems, IO is also treated very much like part of the memory. So for example, if you want to perform a read-write operation on a memory address, you will have an instruction, and the same instruction will also be used for IO. So there is no special instruction available for IO. The IO devices are also mapped to the address space of the system. They are treated very much like the address. And at the low level, there will be a actual translation of the request to the specific to the IO. But from the CPU level, everything looks like memory access without differentiating memory access from IO access. This is called memory mapped IO. And so there are a number of registers involved in the operation. One is data in register, which is used by the host to get the input. Data out register is written by the host to send the output. Status register contains the various status bits which are listed here, whether the current command has completed, whether a byte is available to read, whether a device error has occurred. So all the status details will be available through accessed through the status register, so that the CPU comes to know what is the status of the operation it has assigned to the controller, whether it's finished or it has resulted in some error. That is all understood with the help of the status register. And control register is used to control the operation by giving some special detail. For example, whether the operation has to happen in full duplex or half duplex, whether parity checking has to be done, whether the word length has to be 7 bits or 8 bits, and all these details are supplied through the control register. So various bits in the control register will determine each of these factors. This is just a few samples, but many more operation categories, characteristics can be determined based on the control register. And also sometimes the controllers also have the FIFO chips, which is nothing but to deal with more data. So suddenly, if the controller is overwhelmed with more volume of data, it cannot handle all of them. So it may maintain a queue, just like the CPU scheduling has a queue. There will be a queue maintained by the controller. So the data will be pushed into the queue, and slowly it will be forwarded to the actual device. And then there is an activity called polling. So the need of polling is that so the host repeatedly the complete protocol for interaction between the host and the controller can be intricate, but the basic handshaking is simple. The host in this case implies the specific device. As I told you, a controller is in charge of or supervising a number of devices, and so each device can be treated as a host of a particular transaction. So now how the host can complete its task? It has to go through these steps. Step one is it has to know whether, I showed you a diagram where all the devices are connected to a same cable, which means that only one device can use the bus at a time. Other devices has to keep quiet until the usage of the bus, the first device is over, which is called bus arbitration. So if, for example, if a device wants to transfer some data, it has to first determine whether it's free to access. That is the step one. So the host has to determine whether it's busy or not. So it will check the busy bit. If the busy bit is set, it indicates that that particular controller is busy with some other device data transfer, and so it's not available right now. Step one. Second, if the busy bit is not set, then it sets the write bit, WRITE bit, in the command register to indicate that it wants to write. And also it writes that data into the byte data out register. So basically the host wants to transfer a data to processor, and for that it has to do two things. It has to first set the write bit in the command register to indicate that it wants to write, and secondly it has to push the data into the data out register, and after that it sets the command ready bit. Now the controller notices that the command ready bit has been set by this particular device. It immediately sets the busy bit so that no other device will interfere in this till the completion of this particular transfer. So the busy bit is set, and then the controller reads the command register and sees the write command. It reads the data out register to get the byte and does the IO to the device, and the task is done. And after that it clears the command read bit, clears the error bit, clears the busy bit, and the system is now neutralized. So this is what called as a polling. The major drawback of this particular activity is this step, which is busy bit. Hope you remember we have discussed something like busy waiting. The busy waiting was coming under the topic of the mutual exclusion. So some of the mutual exclusion techniques were employing busy wait. For example, the Peterson solution, the hardware instructions were all making use of the busy waiting. Which technique did not suffer from the problem of busy waiting? Which mutual exclusion technique did not suffer from the problem of busy waiting? I'm looking at the chat window to see whether anybody is typing the answer. Out of the mutual exclusion schemes, which scheme did not suffer from busy waiting drawback? I got the answer from Lohita. It's semaphore. Okay. So see, you are almost at the end of the semester, and you are expecting a MCQ in the next class, and also your university exam can be scheduled anytime. So you have to be having these answers in your fingertip. Okay. So make sure that you are well prepared. So semaphore is a technique which overcomes the problem of, or the limitation of the busy waitings. Since it employs blocking of the process instead of busy waiting. So this particular technique that we just discussed actually suffers from the same problem. So the device has to keep checking the busy bit until it becomes not busy. How do you overcome this? We already know the solution: interrupts. So what happens is that now interrupt has been introduced into the system. So the devices need not have to wait, or the processor need not have to wait for anything. There will be interactions, there will be interrupts made between the devices. So the CPU can interrupt the controller can interrupt the device can interrupt the controller, so and so on. So across, anybody can interrupt to anybody. As a result, you don't need to keep checking for something. You will receive an interrupt when it is become free. So that is the major advantage of the interrupt based system. The previous one is called programmed IO. Of conducting the IO operation is termed as programmed IO, whereas this one is called as interrupt enabled IO. And the story of interrupts need not be explained again. That what is the need of, I mean, what is the idea of interrupt, how interrupts are handled, that is all well known to you. So any device can assert the interrupt signal, and the CPU after execution of every instruction will check whether an interrupt has occurred. If an interrupt is found, then it immediately transfers control to the interrupt vector or interrupt service routine, which contains the necessary code for handling any type of interrupt. All this happens as a response to the interrupt. So these are the requirements of interrupt handling. One is to defer the interrupt handling during critical processing. So there should be masking. You should be able to, the CPU should be able to disable interrupts and when it is doing some critical processing. Secondly, it should have a handler. So there should be handler for handling any type of interrupt. Second requirement. Thirdly, multiple level interrupts. That is nothing but priority levels. So there should be high priority and low priority interrupts, and there should be interrupt controller hardware. Okay, and this is all provided with the help of the interrupt controllers hardware. And I just mentioned about the maskable and non-maskable interrupt. The difference is that non-maskable interrupts are like the ambulances. Okay, they will never be stopped at the traffic signals. Maskable interrupts are like on normal vehicles, though, so they have to wait when there is a traffic signal. So when interrupts are very serious or very critical, they are classified as non-maskable and they will never be disabled. But some low-level interrupts can be disabled if the system is busy with some critical instruction execution. So that is a maskable interrupt. And interrupt chaining is a small idea. As I already mentioned that interrupt handler or interrupt service routine is a repository of all the interrupt handling code. So we have got n number of devices in the computer, and we also have software interrupts. So which means that thousands of interrupts are to be handled by the computer or operating system. So it needs different module of code for each type of interrupt. So the interrupt ISR is nothing but a collection of all the modules. One way of implementing that using a linked list. So the various interrupt modules are linked, and when an interrupt occurs, the linked list is searched to identify the appropriate interrupt module for that particular interrupt. That's what the concept of interrupt chaining. And the trap is something familiar to you. I think the example itself will remind you that system calls. So whenever a process invokes a system call, it gets trapped by the operating system. Similarly, when it makes a privileged instruction call, the process will be trapped by the OS. So when the process is trapped, control transfers to there will be a mode switch from user mode to kernel mode, and there will be a context switch so that the user process is replaced by the kernel, and the kernel looks at the system call, checks which particular module of the OS needs to be executed for that particular call. For example, it may be a fork call, or it may be a shared memory creation call. So accordingly, it executes the necessary library routine, and then it returns the response to the user process, and then the mode transfer is restored to the user mode. That is the idea of a trap. It's a relatively low priority interrupt. Direct memory access is the next advancement happened in the interrupt processing. So these are three different ways of I/O management. One is I/O handling. One is programmed I/O, which is the rudimentary one where there is no interrupts. Secondly, interrupt-based I/O, where you can see there is no need of synchronous I/O. A device can initiate or make a request, and then it can go ahead with some other work. And when the device finishes the task, it will send the interrupt to the host. So that is the interrupt-enabled I/O. And the third is direct memory access. So DMA. DMA adds one more advancement into the IO data transfer. So here what happens is that when there is a need to transfer data between memory and an IO device, it can be input or output. If the data moves from memory to IO, then it's called as an output. If the data comes from device to the memory, it's called as input. Whichever be the case, it involves the processor. In a normal system, the CPU has to fulfill or complete the task of moving data between device and the memory. But in a DMA based system, that task is outsourced to the DMA controller. So a DMA controller is a special device which is capable of performing the IO transfer without the help of the processor. So that is the idea of a DMA. So the DMA is able to do the transfer of data between IO devices and the memory. And the advantage is this saves the CPU time. And there is also a term called cycle stealing. So cycle stealing is a term that is used to describe the situation that when the DMA is making use of the memory, it's also holding the bus, because through the bus only the data transfer takes place. For example, here there is a bus that connects the CPU with the memory, and the same bus connects the DMA with the memory. So when the DMA has been using the memory for data transfer, it must be holding the bus also. And at that time, CPU cannot use the bus. So the CPU is denied the bus access while DMA is already using it. That's called cycle stealing. The next aspect is application IO interface. So how applications interfacing with the IO devices, are connecting to the IO devices. The basic idea is abstraction. So abstraction is like reducing the complexity. As I told you, there are differences in IO devices. Each device, the differences are also going to be listed in the subsequent slide. So each device differs in variety of ways, but the application should be simple to connect with an IO device. It should not be customized for each device. So there is need for abstraction. It is for that purpose we have the system calls. So system calls take care of the abstraction. So when you want to connect to a IO device, you just need to make a system call, and you don't need to know the details of the complexities of the IO devices. So these are the various differences among the devices. So we have got a character stream based device and a block stream based device. A character stream based device transfers one character at a time, whereas a block stream device will transfer blocks of data, bytes. And the sequential or random access. Sequential means that the devices will be, the data will be transferred in a particular sequence, a fixed order. Whereas a random access is like devices can transfer in any order. Synchronous and asynchronous. Synchronous means that there will be a uniform time delay in the data transfer. So the data transfer will take place in uniform delay. Whereas in asynchronous, it can happen at any. It's like when you type on the keyboard, depending upon your speed and mood, you will type the characters, which is asynchronous. Whereas data transfers, when you are copying the file from the disk into the USB drive, it is synchronous. It's going to be copied in a particular rate. So that is the example. And similarly, the devices can be either shareable device or it can be dedicated device. So they are going to discuss about each one of the device. Just go through it once. And one important category is called blocking and non-blocking IO. Blocking IO means that after the IO call is initiated, the process will be blocked till the completion of the transfer. So before the completion of the transfer, the process cannot do anything else. Similarly, non-blocking is that once the IO request is made, and the process can now go on to do something else. So under the blocking system call, the execution of the application is suspended till the completion of the IO, whereas in non-blocking, the application will not be suspended after it has made the IO call. And we have both types of usages in a computer. We have both the blocking and non-blocking usages. Okay, finally, we are getting into the kernel IO subsystem. So kernel is it's a terminology that you should be very much familiar with by now. Kernel is nothing but the operating system, but it's a collection of crucial modules of the OS, excluding the additional modules. If you only consider the core modules of the OS, we term it as a kernel. So the kernel provides many services related to the IO, like scheduling, buffering, caching, spooling, device reservation, error handling. So we are going to discuss about these specifically. First, IO scheduling. See, IO scheduling is more like CPU scheduling. So the same purpose. When you have a single CPU and number of processes wanting to access that processor, you have to schedule them. You have to maintain a queue, and we have to use some algorithm so that you can select the processes one by one. The same is applicable to IO scheduling. So when one single device is being attempted to be used by many devices, scheduling is is inevitable. So IO scheduling is the same idea. It maintains a queue. This is an example of that. Secondly, buffering. So buffering is a memory area that stores data being transferred between two devices. So when, for example, if you are taking a printout, you have connected your printer to your computer, and you are giving some Word document as printout. So what happens is that after you press the print button, the data that needs to be printed does not directly go to the printer. Instead, it gets buffered into a memory region called a buffer, and from the buffer only it goes to the printer. So there are three reasons for this particular usage of buffer between data in a data transfer between two devices. One is to cope with the speed mismatch. I just mentioned the printer usage. Printer is a relatively slow device, and the CPU is the faster device. So clearly there is a speed mismatch, and if you don't provide a buffer between them, the CPU will have to wait for a long time to complete the printing, and that is the reason one, to cope with the speed mismatch. Second is to provide adaptations for devices that have different data transfer sizes. For example, if a device expects only 1 byte minimum to be supplied, and if the source provides bits, then you may have a buffer which combines the individual bits to form a single byte, so that it can be supplied to the device in terms of bytes. So this is another reason. The third reason is something called as a copy semantics. I'll explain copy semantics separately in the next slide. So copy semantics is a simple idea. I think this example is good enough to make you understand this. You just consider the case that a write system call is being executed. Okay, a write system call is being executed to transfer a number of bytes, and so this involves a buffer. So what happens is that after a process has initiated the write system call, all the data is pushed into the buffer, and from the buffer it is supposed to go to the device. Just understand this scenario. A process wants to send a certain number of bytes to a device, and for that it uses a buffer. So the buffer is now filled with the data which was supplied by the process. But problem is that after the data is pushed into the buffer, the process immediately modifies the buffer for some other purpose. See, the buffer may be used for many reasons. So without realizing that the data is still yet to reach the device, the process may override the buffer, or it may modify the content of the buffer. As a result, the actual data will not go to the device. It will only receive the modified or corrupted content which is currently in the buffer. So how to overcome this? And this situation is called as copy semantics. So copy semantics is the ability to ensure that the device receives the original version of the data, not any modified version. Okay. Now, what is the solution? The solution is very simple. There is a buffer called kernel buffer used. So, whenever an application wants to send some volume of data to the device, that data is pushed into the kernel buffer, not into the application buffer. So the kernel buffer is going to be controlled by the operating system. So until the data transfer is completed, be allowed to be modified by the user application. As a result, the data will be intact. So this can ensure that the original data is preserved until it is sent forwarded to the IO device. This is the idea of copy semantics. This may be expected as a 2-mark question or something. So catching is again a common idea you are familiar with. So catching is about speeding up. It's about the usage of fast memory so that you can speed up the data transfer. Finally, they just discuss the difference between buffer and cache memory. See, buffer, okay, I can tell you two differences. One is a buffer is used to hold the data that is needed for the current transfer. It only holds the data that is being transferred right now. But a cache memory contains data that may be needed in future also. It's going to hold not only the currently needed data, but also the data that may be needed in the near future. So it's more extended, number one. Number two, the buffer is maintained in the main memory only. It's not maintained in any other memory. It's also part of the main memory. Whereas a cache memory is a separate memory. It's a faster memory. So these are two differences. You just need to be aware of between buffer and cache memory. And there is another idea called spooling and device reservation. Spooling is a kind of buffer only. It's not a different concept. It's a kind of buffer, but it's only the context in which it differs. See, the context here is that you can take the same printer example. So when I am connecting a printer to a computer, it's going to be simple. My printer will be accessed by that particular computer. But what if the printer is connected to a network? So you may have n number of systems trying to print at the same time. Many computers may want to access the printer at the same time. That is when spooling is needed. So spooling is needed when many systems wants to transfer data to one particular IO device. The data, they are all spooled. It's kind of cube. So all the data gets spooled into a separate files. And one by one, they are transferred to the IO device. Another responsibility of the kernel in the IO management is error handling. So here I just want to point out two important points. One is there are two types of errors that could affect the devices: transient errors, permanent errors. Transient errors are like temporary mistakes, and they can be rectified easily. For example, sometimes you may get disconnected from the internet, or there may be no tower accessing. So that kind of temporary failures are termed as transient errors, and the operating system can deal with them. But permanent errors are more hardware failures. So the operating system cannot rectify the permanent errors. It requires some replacement of the hardware. And so with this, this is just a summary of the various kernel data structures. So the kernel